Welcome everyone, this is Dr. JaskaranSingh, and in this video lecture I will be continuing with the topic of design of rolling contact bearings. In the previous lecture we have already discussed about the fundamentals of rolling element bearings, starting with what are bearings, why do we need them, and where are they used in practical life situations. Then we discussed about the concept of load, types of load a bearing must withstand, namely radial and thrust loads, and we also talked about the concept of static and dynamic loads. Then we discussed that in order to select bearings from a manufacturer's catalog, we need to develop a basic understanding of 5 concepts or terms, which were namely static load carrying capacity, dynamic load carrying capacity, equivalent dynamic load, rated life of bearing in hours, and rated life of bearing in million revolutions. So in the concept of static load carrying capacity, we carried out a detailed derivation of Strybach equation, which is used for the evaluation of static load carrying capacity, and it is denoted as C naught. We then talked about the concept of dynamic load carrying capacity, which is denoted as C. We then moved to the concept of equivalent dynamic load, which is denoted as P. We discussed that we require values of X, Y, radial load and thrust load for its evaluation. And finally, we last finished with the concept of rated life in hours and rated life in million revolutions. So now, moving further, let's try to solve this numerical problem. So the problem is, a rolling bearing has a dynamic load capacity of 26 kilonewton. The desired life for 90% of the bearings is 8,000 hours. And the speed is 300 rpm. Now calculate the equivalent radial load that the bearing can carry. Now, as a standard procedure, it's always good to write down whatever is provided to you in the question. So what is given to us is C is equal to 26 kilonewton, where C denotes the dynamic load capacity. L10H, that is the rated life in hours, is 8,000 hours. N, which is the shaft rotational speed, is 300 rpm. Now, we are asked to evaluate the equivalent radial load, or FR, in the question, which is unknown. Now, the expression for equivalent dynamic load is written as P is equal to X into V into FR plus Y into FA. I hope you remember from the previous lecture that V is equal to 1 in most of the cases in general, as the inner race is always rotating and the outer race is stationary. That's an assumption we always consider while solving bearing numericals, unless or until specified that the outer race is moving as well. Now, since there is no mention about the axial or the thrust load, we can assume P is equal to FR. So we know dynamic load capacity C and the equivalent load P are related by the expression L10 is equal to C by P raised to power small p, where C is 26 kilonewton and P is equal to 0.13, the small p. But the values of P and L10, that is the rated bearing life in million revolutions, are unknown. But we also know that L10, that is the rated bearing life in million revolutions, and L10H, that is the rated bearing life in hours, are related by the expression L10 is equal to 60 N L10H divided by 10 raised to power 6. Now with this information, let's try to solve the numerical. Now, step 1 is to evaluate the bearing life L10, that is the rated bearing life in hours, in million revolutions, sorry. So L10 is 60 N L10H divided by 10 raised to power 6, and we get it as 144 million revolutions. In step 2, we try to evaluate the equivalent radial load. So we know that C is equal to P into L10 raised to power 0.3, and the equivalent dynamic load can be evaluated as 5,854.16 newtons. And since the bearing is subjected to purely radial load, so FR is equal to P is equal to 5,854.16 newtons. So we have completed the numerical. Now, let's talk about the selection of bearing life. Now, while selecting the proper size of a bearing, it is necessary to specify the expected life of the bearing for the given application. The information regarding the life expectancy is generally vague, and the values are based on past experience, values based on past experience are used. For example, the recommended bearing life for wheel applications is given in table 15.1. Now, it must be understood or it must be noted that for all kinds of vehicles, the speed of rotation is not constant and the desired life is expressed in terms of millions of revolutions. Therefore, in other applications, the speed of rotation is relatively constant and the desired life is expressed in terms of hours of service. For example, the recommended bearing life for some of the applications is given in table 15.2. Now, the values given in the above two tables are only for general guidance. For a particular application, the designer should consider the past experience, the difficulties faced by the customers in replacing the bearing, and the economics of breakdown costs. Moving further, we must also understand we need to talk about the bearing designation fundamentals. See, what happens is, while selecting a ball bearing from the manufacturer's catalog, very often a term series of the bearing is used. So some manufacturers use the terms such as extremely light series, medium series, and heavy series, and they are denoted by a number that is 1, 2, 3, and 4 respectively. So for a given diameter of the shaft, the dimensions of the balls and races are smaller in the light series. The load capacities are less and the cost is also less. So with this information, we are ready to understand the bearing series designation. Now, a rolling contact bearing is usually designated by 3 or 4 digits. The meaning of these digits is as follows. The last 2 digits indicate the bore diameter of the bearing in mm. Bore diameter divided by 5. For example, 07 in the bearing series 6307 indicates a bearing of 35 mm bore diameter. The third digit from the right indicates the series of the bearing. For example, 3 in bearing series 6307 indicates a bearing series, a medium series bearing with a bore diameter of 35 mm. The fourth digit and sometimes the fifth digit from the right specifies the type of rolling contact bearing. For example, the digit 6 in the bearing series 6307 indicates deep groove ball bearings. Now we need to talk about the selection of bearing from the manufacturer's catalog. The basic procedure for the selection of a bearing from a manufacturer's catalog consists of the following steps. There are 7 steps in total. Now, step 1 is to calculate the radial force Fr and axial force Fa acting on the bearing and determining the diameter of the shaft D where the bearing is to be fitted. So in step 1, we have to evaluate the values of Fr, Fa and D, that is the diameter of the shaft. In step 2, we have to select the type of the bearing for the given application. It is in most of the numerical questions you will already be provided about the type of the bearing. Now there are a few types of bearings that you must know about. So there are deep groove ball bearings, cylindrical roller bearings, angular contact bearings, self-aligning bearings, taper roller bearings, thrust ball bearing. So moving to step 3. In step 3, we determine the values of X and Y, the radial and thrust factors from the catalog. The values of X and Y factors for single row deep groove ball bearings are given in table 15.4. The values depend upon 2 ratios, Fa and Fr, Fa divided by Fr and Fa divided by C0, where C0 is the static load capacity. Now, the static and the dynamic load capacities of single row deep groove ball bearings of different series are given in table 15.5. Here, I need to make you all need to make a note that the selection of the bearing in this step is mostly done by trial and error. This point will become more clear when we will do some numericals. Now, after this step, we move to step 4, where we calculate the equivalent dynamic load from the equation P is equal to X into Fr plus Y into Fa. In step 5, we evaluate the L10 life, that is the rated life in million revolutions. In step 6, we calculate the dynamic load capacity from the standard formula C is equal to P into L10 raised to power 1 by 3. And in step 6, we check whether the selected bearing of series 60 has the required dynamic capacity. If not, we select the bearing of the next series and go back to step 3 and continue. Again, you need to note down a point that the series 60 corresponds to deep groove ball bearings. We have gone for 6-0 series here, just to give you a hint that most of the tables that are provided in VB Bhandari, they're corresponding to single row deep groove ball bearings. But there can be numericals or questions from other series designations or different types of bearings as well. Now, in order to understand this entire process, let's do a numerical. Now, the question is, a single row deep groove ball bearing is subjected to a pure radial force of 3 kN from a shaft that rotates at 600 rpm. The expected life L10H of the bearing is 30,000 hours. The minimum acceptable diameter of the shaft is 40 mm. Now select a suitable ball bearing for this application. Now, as a standard procedure, we need to note down or provide whatever is given to us in the question. So we are provided that the radial load is 3 kN. The rated life in hours is 30,000 hours. The shaft rotational speed is 600 rpm and the shaft diameter is 40 mm. Now, going by the sequential 7 steps that we discussed in the last 2 slides, step 1 is to evaluate radial load, axial load, and the shaft diameter, which now all these 3 things are already provided to us in the question. So Fr is 3 kN, Fa, the axial force is 0, and the shaft diameter is 40 mm. Step 2 is to select the type of bearing. Again, the type of the bearing is already specified in the first line of the question, that is, it is a single row deep groove ball bearing. Step 3 was to evaluate X and Y. Now in the question we are already provided that it is pure radial load. So Y is equal to 0 and X is equal to 1. In step 4 we evaluate P, that is the equivalent dynamic load. So for a pure radial load we know that P is equal to Fr is equal to 3000 Newton. In step 5 we evaluate L10, that is the rated life of the bearing in million revolutions. We have the standard formula with us and we get it as 1080 million revolutions. In step 6, we evaluate C, that is the dynamic load capacity, through the standard formula. Capital C is equal to capital P into L10 raised to power 1 by 3, and we get it as 30,779.57 Newton. Now with this information, we need to go and have a look at the tables now. So looking at table 15.5, we know that the shaft diameter is 40 mm. And we know that we have evaluated the dynamic load capacity as 30,779.57. So we look into this table and we see that even though in this table there are 6 different bearings that are available for shaft diameter of 40 mm, they are bearing series 61808, bearing series 16008, bearing series 6008, bearing series 6208, bearing series 6308, and bearing series 6408. But for this dynamic load capacity, we can narrow down a search to these 2 bearings, where we can see that our evaluated dynamic load capacity is lying in between these 2 bearing series. So therefore, out of these, bearing number 6208 and bearing number 6308 are suitable for the above application. So that completes our numerical. Now we'll do one more numerical, a little complicated one. Now the question is that a single row deep groove ball bearing is subjected to a radial force of 8 kN and a thrust force of 3 kN. The shaft rotates at 1200 rpm. The expected life L10H of the bearing is 20,000 hours. The minimum acceptable diameter of the shaft is 75 mm. Select a suitable ball bearing for this application. Again, going by the standard procedure, we need to note down whatever has been provided to us in the question. So we're given that the radial load is 8 kN, the axial load is 3 kN, the L10H, that is the rated life in hours, is 20,000 hours, the shaft rotational speed is 1200 rpm, and the diameter is 75 mm. Now, going by the standard procedure for the selection of bearing from the manufacturer's catalog, we need to conduct those 7 steps. So step 1 is to evaluate FR, FA, and D. All these 3 things are already provided to us in the numerical. Step 2 is to select the type of bearing. Again, we have provided the type of bearing in, right there in the first line of the question, that is a single row deep groove ball bearing. We move to step 3 now. Step 3 is to evaluate X and Y. Now in this case, when the bearing is subjected to radial as well as axial load, the values of X and Y factors are obtained from the table by trial and error approach. Now I'm talking about table 15.4 here. Now it is observed from the table that the values of x are constant and the values of y vary only in case when fa by fr is greater than e. So if we have a look at table 15.4, we can have a look here that the values of x are consistent, that is 0.56, but the value of y is changing from 1 to 2 in all these cases. Now, in this case, the value of y, as I mentioned, it varies from 1 to 2. We will assume that the average value 1.5 as the first trial value for the factor y. I hope you remember when I was talking about the theory of going through these 7 steps. In step 3, I mentioned that we need to have a trial and error approach. So this is the point that I was mentioning. So by trial and error, we are just assuming that the value of y can be 1.5, and then we'll conduct the entire process and check if our assumption is true or not. Now, based on this idea, now we have x is equal to 0.56, y is equal to 1.5, the radial force is 8,000 Newton, the axial force is 3,000 Newton. Now we begin with trial 1 and we conduct step 4. We evaluate P, that is the dynamic load, the equivalent dynamic load, by the standard formula, and we get it as 8,980 Newton. We evaluate L10, that is the rated bearing life in hours, in million revolutions, sorry, and we get it as 1,440 million revolutions. In step 6, we evaluate C, that is the dynamic load capacity, and we get it as 101,406.04 newtons. Now, once we get this value for the dynamic load capacity, we need to go to table 15.5 corresponding to the shaft diameter of 75 mm. And we go to table 15.5 for shaft diameter 75. Again, we can have a look that there are 1, 2, 3, 4, 5, 6. There are 6 bearing series designation. There are 6 bearing series that are available for this application. Now we know that the value of C, that is the dynamic load capacity that we evaluated through our trial and error approach, is 101,406.06 Newton. Now if we have a look here, we can see that our value lies in between these 2 bearing series, and even in that it is way very close to this value, that is 112,000. So based on this idea, we will select this bearing. Bearing series for our application, and now we need to check our assumption. So from here we can see that the static load carrying capacity C0 is 72,000 for this bearing series. Now we already know that FA by FR value is 0.357 and the FA by C0 value is 3,000 by 72,000 is equal to 0.04167. Now we will look for this value in table 15.4. We go to table 15.4 and we see that this value of FA by C0 is very close to the value that we evaluated. And we're getting the value of Y close to 1.8. So, and we can also have a look that FA by FR as assumption, we found it, we evaluated to be 0.357 and the value of E is 0.24. So we can see that 0.375 is greater than 0.24 and our assumption is correct. And that's why we will just conduct one trial. And now we'll evaluate the actual, the proper values for the Y parameter, and we'll do it with the help of linear interpolation. Reason being, we know the value of Y at 0.04, but our actual value of E the ratio F A by C0 is 0.4167. So we interpolate it and we get the actual value of Y to be 1.79, and we reevaluate our value, reevaluate the terms, that is P for equivalent dynamic load, and we get it as 9,850 Newton. We reevaluate our C value, that is the dynamic load capacity. We update these values to 111,230.46 newtons. So based on this idea, we can have a look from in table 15.5 that bearing number 6315 is the most suited one for the above application. That is 6315, we get the C value very close to 112,000. And we're getting it as 111,230. So that's why we have selected bearing number 6315. So now we complete this numerical as well. We go to the next numerical So in this example, we are given that a transmission shaft rotating at 720 rpm and transmitting power from the pulley P to the spur gear G is shown in figure 15.8a. The belt tensions and the gear tooth forces are as follows. P1 is 498 Newton, P2 is 166 Newton, PT is 497 Newton, PR is 181 Newton. The weight of the pulley is 100 Newton, the diameter of the shaft at bearing 1 and bearing 2 is 10 mm and 20 mm respectively. The load factor is 2.5 and the expected life for 90% of the bearings is 8,000 hours. Select single row deep groove ball bearing at B1 and B2. So we need to select the bearings at, select the type of bearing B1 and B2 respectively. So again, going by the standard procedure, we need to note down whatever has been provided to us in the question. So we're giving that the shaft rotational speed is 720 rpm, the diameter of bearing 1 is 10 mm, diameter of bearing 2 is 20 mm, L10H is 8,000 hours, and the load factor is given to us as 2.5. Now in these type of numericals, the first step is to draw the free body diagram of the given setup. So we can draw it out here. So we can look here at point B1. Since the bearings are used to support the shaft, so they will act as a simply supported. Setup. So we'll get two reactions here: horizontal and vertical. At point G, since the gear does not support anything but is transmitting forces, and we can transmitting forces, so therefore we'll get two forces here: the radial component of the force and the tangential component of the force. At bearing 2, again, because it is supporting the shaft, we'll get two reactions, RH2 and RV2. And at point P, the place we will where we have the pulley, we have the weight of the pulley acting in the negative downward direction, and we have the tension forces, the sum of the tension forces P1 and P2 acting in this direction. Now once we are clear with the free body diagram, we need to basically consider the forces acting in the vertical direction. So we will first consider the forces in the vertical direction, and then we'll consider the forces in the horizontal direction. So first, considering them in vertical direction, which are the forces acting in vertical direction? It is PR, the weight of the pulley, RV1 and RV2. Now based on this, taking moments of force about bearing B1, so we can write this equation, that is PR into 100, W into 400 and RV2 into 250 is equal to 0. We know that PR is 181 and W is 100, so we can put them back in the equation and get RV2 as 232.4 Newton. Now we need to do the equilibrium of forces in the vertical direction. So we can write down RV1 plus RV2 is equal to PR plus W. We can put down the values we know from the data given, and we can evaluate RV1 as 48.6 Newton. Now we need to repeat the entire procedure for horizontal direction as well, and we know what are the forces acting in the horizontal direction. It is P2, P1 plus P2, RH1 and RH2. So taking moments of the force about bearing B1, we can write down the equation that PT into 100, P1 plus P2 into 400, RH2 into 250. So we know that PT is 497, P1 is 498, P2 is 166 Newton. Putting them back in the equation, we can evaluate the value of RH2 as 1261.2 Newton. Now equilibrium of the forces in the horizontal direction, we can write RH2 is equal to RH1 plus PT plus P1 plus P2. So we can evaluate RH1 as 100.2 Newton from this equation. So we have evaluated all the support reactions in the last two slides. Now the reactions at the two bearings are given as R1, that is the resultant here in this case. That it will be underscore of RV1 square plus RH1 square, and it is equal to 111.36 Newton. R2 will be equal to under root of RV2 square plus RH2 square, and it will come out to be 1282.43 Newton. Now the bearing reactions are in the radial direction, therefore we know the radial forces acting on the bearing as R1 is equal to 111.36 Newton, and the radial force acting on bearing 2 will be 1282.43 Newton. Now the next step is, so this becomes the step 1 of the 7-step series that the 7-step sequence that we are doing in the that we have been doing in the last two numericals as well. That is for the selection of bearing for the manufacturer's catalog. The step 1 is always to calculate the radial and axial forces acting on the bearing and determining the shaft diameter where the bearing is to be fitted. So right now here we know that the radial forces for, like, considering bearing 1, we know that the radial force is this much. There is no axial force acting on the bearing, and the shaft diameter is 10 mm. Likewise, for bearing 2, we know that the radial force acting here is 1282.43 Newton. There is no axial force acting on the bearing, and the shaft diameter is 20 mm. Now the step 2 is to select the type of the bearing. We already have been provided that it is single row deep groove ball bearing. Then we move to step 3. We try to step 3, we know that since there is only radial force acting on the bearing and there is no axial force, x will be equal to 1 and y will be equal to 0. So we move to step 4, which is basically to evaluate the equivalent dynamic load. We will do it individually for both the bearings. We will get P1 as 111.36 and P2 as 1282.43 Newton. So we go to step 5, which is to evaluate the L10 or the rated life of the bearing in million revolutions for each of the bearings, and we'll get L10 as 345.6 million revolutions. It will be same for both of the bearings. And in step 6, we go and evaluate the dynamic load capacity of the bearings, and we'll get it as P1 into L10 raised to power 1 by 3. For bearing 1, we'll get the dynamic load capacity as 1953.71, and for C2, that is dynamic load capacity of bearing 2 as 22,499.09. Now you must notice here that we have a term known as load factor here. So what is this load factor? See, the forces acting on the bearing are calculated by considering the equilibrium of forces in vertical and horizontal planes. Now these elementary equations do not take into consideration the effect of dynamic load. The forces determined by these equations are therefore multiplied by a load factor to determine the dynamic load carrying capacity of the bearing. So that is what this term represents, to take care of the dynamic forces acting on the bearing. All right. So in step 7, we go to table 15.5, and the same procedure that we have been doing in the last two numericals. We try to select the bearings, and I don't have the table right now here. So the bearing numbers that you can cross-verify from the book, you will get bearing numbers 6000 and 6404, which are suitable at B1 and B2 respectively. So we complete numerical here. Now moving to a new concept, that is bearing with a probability of survival other than 90%. See, you need to understand that in the definition of rating life, it is mentioned that the rating life is the life that 90% of a group of identical bearings will complete or exceed before fatigue failure. The reliability R is defined as R is equal to number of bearings which have successfully completed L million revolutions divided by the total number of bearings under test. Therefore, the reliability of bearings selected from the manufacturer's catalog is 0.9 or 90%. But in certain applications where there is risk to human life, it becomes necessary to select a bearing having a reliability of more than 90%. So this figure here shows the distribution of bearing failures. The relationship between bearing life and reliability is given by a statistical curve known as Weibull distribution. Now for this Weibull distribution, we have the value R is equal to exponential to the power of negative L by A raised to power B. Now where R is the reliability in fraction, L is the corresponding life, and A and B are constants. Rearranging the above equation, we have 1 by R is equal to E raised to power L by A raised to power E is the exponential term, L by A raised to power B, or we can rewrite the equation in this form. Now if L10 is the life corresponding to a reliability of 90% and if L10 is the life corresponding to a reliability of 90% or R90, then log to the base E in brackets 1 divided by R90 is equal to L10 by A raised to power B. So rearranging the above few terms, we'll get this equation, where now you just remember that this particular equation, the L by L10 equation in this blue box, now this is used for selecting the bearing when the reliability is other than 90%. Now this is something we'll use in the numericals. Also, if in a system, if there are number of bearings, the individual reliability of each bearing should be fairly high. If there are n bearings in the system, each having the same reliability R, then the reliability of the complete system is given by Rs is equal to R raised to power n, where Rs indicates the probability of 1 out of n bearings failing during its lifetime. Now, with this idea, let's do one numerical. Now, a ball bearing subjected to a radial load of 5 kN is expected to have a life of 8,000 hours at 1415 rpm with a reliability of 99%. Calculate the dynamic load capacity of the bearing so that it can be selected from the manufacturer's catalog based on a reliability of 90%. So again, we need to first, whenever we begin a numerical, we need to note down whatever is provided to us in the question. So Fr, that is the radial load acting on the bearing, is 5 kN. The shaft rotational speed is 1450 rpm, and we are provided with L99H in this case, which is 8,000 hours. Now the step 1 is to evaluate the bearing life with 99% reliability. So we can write L99 as 60 N L99H divided by 10 raised to power 6. So we'll get it as 696 million revolutions. In step 2, we need to evaluate the bearing life with 90% reliability. I hope you remember the formula in the blue box that I mentioned just in the last slide. So we'll make use of that formula and we'll put down all these known variables and get L99 by L10 ratio as 0.1342, and we'll get L10, that is the rated life of the bearing in million revolutions, as 5186.29 million revolutions. So in step 3, we'll evaluate the dynamic load carrying capacity of the bearing, that is from the standard formula, and we'll get it as 86,547.7 Newton, 47.7 Newton. So this completes this numerical. This is what was asked in the numerical. So this completes your topic on rolling element, the design of rolling element bearings.